This is an introduction to the idea of Lewis dot structures, and it's called What's with All This Dots? And you have I must continue my quest for this to slay the red dot. Lots of cats like to chase little red dots around. So it says I think that there's a little bit of sizzling here. Honestly, I can feel the ions flying back and forth. That's a quote by Regis Philbin. So we're going to talk a little bit about electrons and ions kind of flying back and forth. So the first thing is we want you to be able to demonstrate ionic bonding using Lewis dot structures. And you also should be able to demonstrate covalent bonding using Lewis dot structures and Lewis covalent structures as well. So the first thing is the octet rule. Okay, atoms are stable when they have filled valence electrons. So what we say is we say that everything is going to be stable when it has 8 electrons in its outermost level. And the reason why we say that is when it has 8 electrons in its outermost shell, that puts it in group 18. It fills the s orbital 1 and 2 and the p orbital 3, 13, 14, 15, 16, 17, and 18. So as a result, whenever it satisfies the octet rule, it is in what we call the noble gas stage. So most atoms want to be in the noble gas state, so they are satisfied when they have 8 electrons that surround them. Now, this is mostly true for elements that are below 36, but that's what we deal with in this class. We tend to not deal with the super heavy elements or anything like that. So, because of that, we say that almost everything is going to satisfy the octet rule in this class. Now, there are two major exceptions, and that is hydrogen and helium. They are stable with only 2 electrons because remember, they have just 2 electrons in their inner shells, and that's what they're actually happy with when their s orbital is filled. And that's why you tend to see them right here. They're in this top row. Whenever you have the top row there, as a result, um, as a result of them being in the top row, they're satisfied with only 2. That's why there's only 2 in that one orbital. So, Lewis dot structures. And since chemists for the most part are interested in the valence electrons, that's the outside layer of electrons, we tend to draw these things called Lewis dot diagrams. These Lewis dot diagrams represent the valence electrons. Now remember, lithium actually has 3 electrons. Okay, but 2 of those electrons are in the inner shell, and it only has 1 electron in its outer shell. So for its Lewis dot structure, I only draw the 1 electron that it's in its valence shell. You see, I draw 1 for lithium, I draw 2 for beryllium, I draw 3 for boron, I draw 4 for carbon, and I draw 5 for nitrogen. You may say, well, how do I know that that's how you do this? If you look at the periodic table, you would say, okay, well, here's lithium in the second row, and it has 1 electron. That's why it's in column 1. Okay, beryllium has 2 electrons. That's why it's in column 2. When you skip all the way across the transition metals to 13, you see that in 13 you've got boron, and boron has 3 valence electrons, hence 13. Carbon has 4 valence electrons, hence 14. Nitrogen has 5 valence electrons, hence 15. So as a result of that, you can see that the valence electrons have a lot to do with the organization of the periodic table. And we do fill these electrons according to Hund's rule. Example A1. It says the octet rule is really more of a general guideline than a rule. There are certain elements that are more stable with more or less electrons. So, using your knowledge of electron orbitals, speculate as to why this is the case for boron trichloride. If you look, boron has 1, 2, 3 valence electrons. So, whenever boron tries to form a bond, it can form a bond with 1 chlorine, and then it can share. It can do the same thing here, and it can share, and it can do it here, and it can share. And if you look at it in this case, boron has used all of its available electrons, but it still has this gap right here where it could fill something else. But it would require an element coming in and contributing 2 electrons to it and staying stable. Well, the only thing that can really do that is a noble gas, and noble gases don't really want to bond with anything. So as a result, boron trichloride is much more common than boron tetrachloride. Now, you could force boron tetrachloride to occur, but it tends to not as easily and will easily fall apart. Draw the Lewis dot structure for selenium. So the easiest way to find the Lewis dot structure is to come here and find selenium on the periodic table. And if you look, selenium is in group 16, which is and it's just below sulfur. And so we would take selenium, we would say it's in group 16. So since it's in group 16, we would say it has 1, 2, 3, 4, 5, 6 electrons. And so this would be the Lewis dot structure for selenium. Example A3 says you have a new element that's discovered with the electron dot structure here, and you have element XYZ. It says what chemical family does this belong in, and then what you do is you count the Lewis dots. So you say 1, 2, 3, 4, 5, 6. Since it has 6 dots, that means it has to be in family 16, which is the chalcogens. Okay, everything in group 16 has 6 valence electrons. So it could be oxygen, sulfur, selenium, tellurium, polonium. It could be any of those right there.